Okay, guys, I think we can start today's session. Last class, if you remember, we have started discussing about the Lino board, okay, which is one of the Hobbyist project. Um, it is actually an autonomous mobile robot, which is done in ROS 1 and ROS 2. Okay, so we have actually seen what are the electronics inside that robot, what are the boards, then what are the computer, all these things. We will be starting from that point, and then we will be seeing the software stack as well, how they set the navigation. We will be also seeing the Turtleboard 3. So when I try to set the navigation for these two robots, I think there is a bug in the navigation stack. Somehow it's showing the same error. It is the navigation is not starting. Unfortunately, it shows a map, but maybe I can show you that. But mapping is working. Okay, Slam is fine. We are not discussing much deep into the navigation stack. We will be seeing just basic, and then we have a chapter coming here on the mastering session. We have mastering navigation stack 2 is there, movie 2 is there. Okay, so in that time we will be discussing that in detail, and also we have a mastering ROS 2 deep learning session. So we will be trying to work out some more examples because we already discussed the concept, but we will be seeing like the TensorFlow, PyTorch, all these stuffs are new, but we will be seeing that. Okay, and yeah, okay. So let's start with the Lino robot that we have seen yesterday. Okay. So the agenda of this chapter is basically creating an autonomous robot for any purpose. Currently, I just put it as like food delivery robot. That is, like the robot can able to bring the food from one point to another. Okay. So I'm just taking the project. So you can also check the project in the GitHub. Um, and I'm just taking the hardware that we have discussed. So you will get a continuity. Okay, so it's basically a two-wheeled robot. Maybe I can show you that. You can configure the robot in multiple configurations, like four-wheel, two-wheel. You can configure. So this was the electronics circuit, or we can call it as a system diagram. Okay, so just start from here. So inside the robot, you can see there are like four motors basically. Okay, four motors. So you can configure the robot into a four-wheel drive or a two-wheel drive. So this is actually for a four-wheel drive. There is no difference. Like for the two-wheel drive, there are two motors will be missing. Okay. So just look at the configuration. I think it's very clear and very easy to you. Like there is a microcontroller. It can be like TNC board or a Raspberry Pi Pico, all this board we have seen yesterday, and this can be easily connected to the motor driver, because these microcontrollers having PWM pins or digital pins. I think you have a basic understanding of microcontroller. It is having IO pins, input output pins, in which we can set the pin to high and low. Okay, and there are some pins which is dedicated for PWM, pulse width modulation, which is actually used for, I mean, one of the application of PWM is like in robotics. You can control the speed of the motors through the motor driver. So if you take a motor driver, there are some examples of the motor driver. Yeah, so this is a typical motor driver. It's called L298, very common motor driver. So you can see um, the motor drivers having set of pins to to uh, to give the PWM. Okay, so these are the pins you can see here. These set of pins are the PWM pins. Okay, so there are certain pins that we can use or configure for the for PWM, and similar to that you can also watch this example. So because they are actually showing multiple example uh, of the motor interfacing. So here on the left side microcontroller, and it is connected to the PWM. I mean, each pin of the microcontroller is feeding to the PWM. Okay, so that we can adjust the PWM, and thereby the motor driver will be adjust the speed. Very simple. Okay, and the motor will have, there are two set of configuration for a DC motor. Maybe the motor will have an inbuilt encoder. Okay, wheel encoder, I think you already know it. The wheel encoders are basically a feedback sensor in order to find how many rotation that wheel actually taken. Okay, so in a DC gear motors, when the wheel rotate, I mean, if you are connected a DC gear motor into a robot wheel, when the robot moves, this encoder will be ticking, and we are getting a pulse basically, and using that, these pulses are feeding to the microcontroller. Okay, so the microcontroller will be interrupting. For example, when the input or the output from the encoder is actually simply pulses. Okay, so when it moves a certain degree or something, it will be creating a certain pulses. So the microcontroller can be configured to receive these pulses, and you can configure the microcontroller like interrupts. For example, when a pulse comes, the microcontroller will be interrupting, and then it will be counting. Okay, so we basically need the count. So each motors in this diagram is configured like that. Okay, so there is an encoder, interrupt pins. For if there are 4 motors, there are pins we need to interface for the encoder, which is like an input to the microcontroller, because encoder is actually a sensor, robot sensor. And on the left side we have the PWM pins to output the PWM into the motor driver in order to control the speed of the motors. Okay, I hope that is clear to you. And the microcontroller is running on micro ROS that we have discussed yesterday. So the micro ROS is very similar to the ROS serial. Basically, we are writing the code on the microcontroller using micro ROS APIs. So micro ROS is like a micro version of ROS 2, in which you can use RCL-C APIs to program the controller. Okay, and using that you can like publish, subscribe, all this stuff you can do. And the microcontroller is connected to a robot computer. It can be a Raspberry Pi or Jetson Xavier or Jetson Nano or any other board. So it is connected to the robot computer through USB to serial basically, and the robot computer is running the micro ROS agent, which can able to decode and encode the data to the microcontroller and can see the topics of microcontroller in the robot computer. Okay, so basically in the robot computer you can see the encoder values, IMU value, then you can also publish the motor speed which will be going to the microcontroller. Okay, and on the right side of the robot computer we have bigger sensor, like the sensor that can't be interfaced to a microcontroller, which are laser scanner, depth sensor, and if you have any other sensors, like you can directly plug into the USB hub. Okay, so this is the configuration. I hope it is clear to you. I'm just sharing the link so that you can also check. So we have completed the electronics part, which is the important part, and then you can see the micro ROS programming. Okay, so that is the next thing that you are going to see. So micro ROS here, the project actually used Teensy board. Okay, Teensy board, which is kind of like we can program using the Arduino IDE. Okay, and if you just check the code, okay, we can simply go through the code. Just go to the firmware folder, and go to the SRC folder, and this is a firmware. Firmware means the micro roast code that we have to burn into the microcontroller. Okay, so initially if you take this code, I mean, it's somewhat confusing to you because you didn't work with the micro rows yet, right? I just explained it yesterday, but if you already know the row serial, then you can do a comparison. Okay, basically here they are using the Teensy board, and yesterday we have seen how we can program the Teensy with micro rows. Okay, we can download the Teensy Duino, which is the Arduino IDE for Teensy. Okay, I'm sharing the link, so you can have a look how we can program the Teensy board. Okay, and we also have seen the basic publisher and subscriber for Teensy. Okay, so this is the same API, or like the MicroRose Arduino node. MicroRose Arduino is what used in the Lenovo robot. Okay, so you can simply see the header file like MicroRose platform IO. One more point to add. So I'm not explaining the code in detail and how to compile. I will give an idea actually. Okay, so you have to, I mean, check as well. Okay, so in order to compile these micro rows code in Teensy, we can either use the Teensy Duino, or I'm not sure you heard about the Platform IO. Okay, Platform IO. Platform IO is actually a plugin. I will say, yeah, it's a plugin for embedded software development. Okay, I have used it. It's very good. It's actually used in professional embedded software development. Okay, it's free. What you can do is, like, you can simply install VS Code and you can install the Platform IO plugin, and you can easily program most of the embedded boards using this. Okay, so I'm just giving the link as well. So it seems like the author of this project used the Platform IO for programming the robot. Okay, so the code is actually very straightforward. If you check the Arduino code, you can able to see the void setup function and void loop function. Okay, so these are the main function that we are able to see in Arduino code, right? So inside this void setup, they are actually like in the microcontroller. There are two sets of sensors available. One is the encoders, and then is the IMU. Okay, so here they are on the setup. They are actually starting the IMU and then flashing some LED and then starting. These all are I mean, they are starting the serial communication and then some micro row serial transport. I will come to this. So, and also in the loop, what they are doing is they are actually this is actually happening in the microcontroller. Okay, so they are waiting for the agent. Okay, so in the loop means it's the loop continuously working. Okay, so they are working, or they are continuously waiting for the agent to get started. Okay, so where is the agent locates? The agent is in the computer. So whenever the agent starts, then it will be I mean, detecting it, because the microcontroller is always pinging to particular port, and then if that port actually started by the agent, then it will be showing agent connected. I mean, it will be showing the messages agent connected, and then it will be doing the spinning. Spinning means, right, in the rows 2, like when rows, the spinning means it will be waiting. for the publisher and subscriber, or all the things. Okay, so for we can check the set micro serial transport. One second. Okay. Yeah, I think, yeah, it's actually a micro rows API, it seems. But what we have to give importance is that if you just see here, you can see the publisher, then subscriber. Okay, these all are the objects. We can say it's all are the objects, and we can see the messages which want to publish. Okay, and there are executor and allocator. Executor and allocator actually, like executor in rows 2 is basically one of the basic example for executor is the spin. So what spin does is that the spin is actually waiting for the callback in a single thread. Okay, but you can actually run the node in different thread as well. So you can write executor to configure the execution of your node. Okay, if you just want the single thread execution, then spin will be enough. Okay, spin is a kind of execution. Okay, so yeah, so all these things actually defined globally, and there are some modules or header file in which we can directly give the or we can directly create objects for like encoder, motor, PID, kinematics. All these things, I think the author actually created. These all are these libraries are created by the author in order to make the code easier and readable. Okay, so if you want to start an encoder, just create the object of it, just give the pin number, and then you can work on an encoder. Okay, and also this kinematics class basically can convert the command velocity to the motor velocity, something like that. Okay, so all these things happening, and in the loop you can see it is waiting for the agent. Once it get the connection, then it is spinning. Okay, so so you can able to see like yeah, so this is a main stuff, and also you can see this function called create entries. So just see here, if the agent is available, for example, if the agent is running, I mean it's not just connected, if it is available, then it will be calling a function called create entries. It's basically like an initialization function. It will be like creating the publisher, subscriber, here's IME publisher, you know the purpose, right? IME publisher will be published the IME value, then this is publishing the ODOM value from the encoder. So then there is a timer callback. All these things are initialized. Okay, so once it initialized, then we can see the callbacks, all this stuff. Okay, you can see the publish function, all this stuff. Okay, so the code, the micro rows code that we are seeing is basically it is like initializing. If you check the void setup, it is doing some initialization of the serial port, and then in the while loop, in the loop function, it is constantly checking for the agent. Okay, if the agent, micro rows agent in the main computer is started, then it will be starting the publisher. Okay, it will be initializing the publisher and listening to the callbacks. Okay, and all the publisher objects are defined here. Okay, so this is like a sneak peek of the firmware. Okay, and you can see other libraries I think he included in the lib function. Yeah. So these all are the libraries available. You can see the .h and .cpp file. So it is very modular. So the code will be looking, I mean, you don't need to include all this stuff in the same code. You can create the modules like this, so the code will be readable. Okay. So this is the firmware code. So what you have seen was the main code that we have to burn into the microcontroller. So it's basically a publisher and subscriber, and also like it is subscribing to the command velocity, and the command velocity is converting into the motor speed. Okay, and they are also guiding you to set up the platform IO. So the platform IO is the IDE or the text editor the author has used. Okay. Okay. So now we can jump into, so assume that we have burned the firmware, okay, into the microcontroller. Now it's a ROS part. Okay. In ROS, what we have to do? Okay. So once we connected, once we connect the microcontroller to the main computer, which is on the top, okay, robot computer, the agent actually read from the microcontroller and publish and subscribe the topic. So whatever the topic is publishing, odometry and IMU, and the agent will be subscribing the command velocity and send to the microcontroller. Okay. So so what are the other stuff happening? So there is an EKF robot localization package actually configured in order to get the better estimate. Okay, so the IMU and the odom value, wheel odometry, is getting fused, and then the EKF will be publishing the TF and the odometry, odom topic. So these things are going to the nav2. So the nav2 in concept wise is same as now navigation stack in ROS. Okay, the ROS one, but the architecture changed, but it's simply nothing but we the navigation stack is getting the sensor data like laser scan, then point cloud, then what are the other inputs, odometry, all these things, TF, then AMCL, all this stuff going to the navigation stack, and the navigation stack also getting the map as the input. Okay, because it need actually a map to navigate. Okay, so what is the output of the navigation stack? Is the command velocity. Okay, so nav2 is an entirely, I mean, it's a very time consuming topic, I will say. It will take time to explain it. So in my case, in this project, they have given the navigation package, then gazebo, then description, the bring up, all these things. Okay, so I have actually ran this code for navigation. Unfortunately, navigation is not working for me, but we can have a look. Okay, so I will be setting the code now, and we can also see the turtle board. Okay, so these are the two things we are going to do now. We are going to set up the code. We are going to inspect the code, what is happening. Okay, and we will go through, like we can simply go through it, not explaining in detail, but just seeing what is happening. Okay, so let's start setting the code. So what I can do is I'm just creating a new workspace for now. Lino Robot 2 workspace. Okay. Then I'm creating a new SRC folder, and I'm just cloning the code. Okay, I'm just cloning the code. Let me install it. 1 second. So I'm mainly cloning the simulation code. Okay, not the actual hardware stuff. So let me yes, So inside the SRC, I'm just cloning this. 1 second. So you can see the instruction here. I'm just following it. So we are looking for the gazebo simulation. Okay. And yeah, we have cloned it, and now it's a command called row step, which will be looking for the dependencies. Like if there is any dependencies that need to be installed, it will be installing that automatically. So it seems like all the dependencies got installed, and now you can build it. Okay, it's got built. Now we can source it. Install. One second. Yeah. Source Lino Robot 2 workspace, then install, then setup.bash. So this is the command. Now bash rc, I'm just putting on the bash rc. I already set up Turtleboard 3 also, but it is also not working. I mean, not the simulation, but the navigation, but we can see. Okay, I'm doing a experiment now. Okay, so we have set it up, and then they are saying we need to configure what kind of base that we need. Okay, we need a 2-wheel drive or 4-wheel drive. That is the next thing that we have to set up. So maybe I can go with the 4-wheel drive, because I tried with 2-wheel, which is showing the simulation, but the navigation is not working. Okay, so what I'm doing is I'm just setting this variable to 4-wheeled. Okay. Okay. Now I'm just sourcing it. Okay, and we also need some packages for the visualization. Workspace, okay, SRC. So it's called Lino Robot 2 Viz. Again, we have to install the dependencies. Okay, so it seems like installed, but the micro ROS agent is not installing because we don't need it actually. Okay, and again doing the callcon build. Okay, okay, I think we already set everything. Now what we are doing is we set up all the packages for simulation, navigation, all the stuff. Now we can check the description. Description means just visualizing the robot model in RViz. Okay, so this is the robot model. You can see 1 second. Yeah, like 4-wheel, and you can see the laser scan, and on the top we have the camera. Okay, a depth cam. Okay, so the description is fine. Now what we have to do is we can start the simulation. Okay, so let me start the simulation. Let's see what will happen. Okay, seems like okay. So I already spawned the Lino board before. That's why it is loading quickly. But if you are doing it first, it will take some time to download these models, and yeah, it will take some time. Okay. Okay. So here is our robot, which is actually putting in a playground. Okay. Now, uh, first we can do some teleoperation. Just make sure the robot is moving or not. Okay. Okay. So oh, I'm just okay. Okay. Fine. So we have a teleop node in the package. Teleop. We have to use u yeah uj yeah these keyboard keys. Seems like it is moving. That is good. Okay. Now, what we can do is we can also visualize. Okay, what are the sensors that is giving. Okay, so this is very important, guys. So we are simply moving the robot, and we are trying to visualize the sensor data. Okay, so what I'm trying to do is I'm just checking if there is any visualization thing. Navigation minimal. Okay. Okay. I'm just checking with some RViz configuration so that I can see the visualization. And see, you can see here, this was one of the issue that I got. The laser scan is there, but it is not showing. Okay, it's not showing. So I was checking for the issue. Like you can see, the laser scan is not showing, and I just want to check the other stuff, like whether I'm getting the image or something. Let me check. Yeah, image is actually getting image. All the stuff is working. Okay, so the camera is working, but the laser scan is not. So what I'm doing is I'm just closing this everything, and then I'm just going to the workspace, and then going to the description, URDF, sensors, and the laser. Okay, so if you worked before, like if you have GPU, then this GPU ray will be working. Okay, so this is actually the plugin, laser scanner plugin, similar to the ROS one. If you want to add a laser scan in the simulation, we have to add the Gazebo ROS laser scan laser.so. Here is ROS ray sensor, both will work. So the GPU ray will not work in my case because I'm working from VMware. Okay, in your case also you can try. If it is working, then it's fine. Otherwise, just remove the GPU from the ray. So sensor type is just the ray. Okay, after that you have to do the build again because we changed it. Do the Qualcomm build. Now start the Gazebo. Oh, sorry, this is for the turtle board. Yeah. Okay, here the simulation. Now let's start the RViz. and load the change to auto. Yeah, so now you can easily see the laser. Okay, so this means that you can go to the navigation now because the sensors are doing fine. We are getting the laser scan, which is very important for the navigation stack, same as the ROS one. Okay, so next we are going to start the mapping. That is the first part, right? If you already have the map, then you can use it. Otherwise you have to map it. Okay, so mapping is easy. In ROS 2 we have the SLAM toolbox. Okay, one second. We have the SLAM toolbox, okay, which was already there in ROS 1. Okay, but we were been using the G mapping, but SLAM toolbox is slightly better. I mean, it's modular and you can use I mean, you can save it and then do the mapping after that. So it is good for mapping a big environment. Okay, when I tested, the mapping was working with me when I tested. So let's see the mapping stuff. Okay, the mapping, I think it started, and now okay, so what we can do is there is an option to start the map with the RVs. Okay, that will be better. So you can see this is how we start the SLAM, but yeah, so if you are using this command, it is actually like starting the RVs and using that in the simulation. Okay, one second. Okay, so now you can see the mapping it just started. Okay, and you can use the teleop. Using the keyboard you can able to move it. You can see it is building the map, 2D map. I'm just moving around. Just check that the localization is actually very good. It's even if the robot is moving in a particular speed, the mapping is actually very robust. Okay, yes, so it seems like it is building the map, and so if you want to save the map, again we have the map saver. I hope you remember it. Just use this. Like, one second. We have the ROS 2 map saver. So the map server is the thing that is saving it. So I'm just giving new, the name as new. Okay, so this is a command, and the map got saved. Okay, so this is the map. Okay, so the procedure is similar or exactly same as the rows one. Okay, so this is why I actually try to teach you rows 1 first, because now you know what is happening in rows 1 and rows 2. Okay, so now we have mapped it. Next is the navigation. Okay, so that is where the problem comes. So let me try it. Okay, let's see what happened. So what I will do is I will copy the map into the home folder just for a test. Okay, so the map of this environment is already there in the in the maps folder. So what I will do is I will be pasting it. Okay, and then I'm starting the simulation and the navigation. Okay, there is a launch file for that. Okay, so we have started it, and now we can start the navigation. So this is the launch file called navigation.launch, and for this launch file we have to mention the path of the map file. That's it. Okay, so just give the name. What is the name? Playground. Okay, playground.yml. Yes. So let's see what will happen. Okay, so it seems like there's a problem. What I can do is I can also enable the thing like rv is equal to true and sim equal to true. Let me see if there is any change happen. Okay, so you can see the map just came, but it's actually complaining about TF. Okay, the TF, and you can see in the RVs the localization is actually not working properly. So that is what my understanding. So all these things are coming, but yeah, so this is a situation. I actually updated the repository and all, so I'm not sure because this is an already existing project. It's actually a working project, but you know we are getting the issues like timeout waiting for the transform from base link to map to become available. So it seems like yeah, invalid frame ID map. I'm not sure the error, why the error. And also I have seen the AMCL error, like the AMCL cannot publish a post because AMCL is what publishing the TF with respect to the base link. Okay, the map TF. So you can also inspect this issue like using RQT. We can see the node graph. So what is going on? 1 second, I'm starting the RQT. So regarding the TF, you can clearly see the map TF is not there. Okay, only the ODOM base footprint is there. So the mapping or the AMCL is not at working good. And if you check the node graph, we can see what is going on. Let's see. Yeah. So okay. So the AMCL, it seems like the AMCL is not working good. That is the message it's showing, but it started all the stuff. You can see here we have the IMU coming from the gazebo, and EK filter, then local cost map, global cost map, all this stuff. Okay, and yeah, there are some other nodes from the nav2. So this is a situation, guys. I have tried multiple times. You can also try. I'm not sure it is the issue here. I didn't get time to fix it. That's why. Because I'm assuming that even I tried with the Turtleboard 3, so it is popping up with the same error. And I'm using the latest version of the Humble packages. Okay, maybe this can be solved by changing it, by changing some parameters in the navigation stack. I can do some hack. Let me see if that works or not. So what I'm doing is I'm just going to the navigation stack configuration. So we have a YAML file for the configuration of navigation stack. So if you remember, in navigation stack 1, we were writing different YAML file for local cost map, global cost map, then the planner, all this thing. But for the navigation stack 2, they have the similar component. I will be showing the architecture, but we can simply include everything in a simple launch file. Okay, not launch file, YAML file. Okay, so they are complaining about the map. So what I'm doing is I'm just adding map frame like this. I'm not sure, it's just a hack. Okay, so let me just try again. I'm starting the navigation. Simulation is already running anyway. Okay, let's see. Okay, no, it's showing the same thing, and the map is loaded by the map server, but it's showing the same stuff. Okay, I think it's problem with the AMCL. I need to check it why this is coming. The same thing happened for the Turtleboard 3. Okay, so what we can do is I'm just quitting this, and then I'm just going to the navigation stack, new navigation stack, which is nav2, and then we can see what are the things happening in nav2. Okay, so just want to give you one second. Yeah, so this is the official website. I hope you may have seen it. So it is actually the successor of navigation stack 1. We have played around that before, and this is the architecture now. Okay, the same stuff that we are working before, like it is having the planner, then the cost map, all this stuff, but there are some add-ons and there are some updates. Okay, the main thing is that here you can see in navigation stack 1 we have the move base. I think it's move move base. Okay, which is actually a node it's not an exactly a node. We can say it is a nodelet. Okay, and nodelet or a node. Okay, and you can load the plugins into it. Okay, so it's a node which can be I mean, we can actually load the plugins into it. So what are the plugins of the navigation stack one? Maybe I can take it. Okay, navigation stack. Okay, yes. So yeah, so this was the navigation stack one architecture. So basically we have the move base node, and inside that there was several plugins for global planner, local planner, global cost map, local cost map. Okay, and recovery behavior. So this is navigation stack, and the input you can give like this. Okay, like the map is an input, laser scan, point cloud, all this input, then odometry and TF. Okay, so the input to the navigation stack is a goal position. So imagine you are giving a goal position through GUI or program. Like you are simply giving the goal position where the robot want to go. Okay, and the output, what is the output of the navigation stack? It will be publishing the command velocity to reach that position. Okay, so this is the navigation stack 1, and this is the navigation stack 2. Okay, so just compare the architecture. So we have a new thing called behavior trees. Okay, and a new concept, there is a new concept in ROS 2 called life cycle nodes. Okay, so life cycle nodes, what we can do is, like in the life cycle node, if you are using life cycle node, okay, it's actually a node very similar to other nodes, but the difference is that you can actually start, stop, pause, like you can change the state of the node. Okay, for example, you started a lifecycle node, and you can actually start it. Start it means what? Imagine you are going to drive a car. Okay, if it is a manual car, once you start the car, it will not move. Okay, it will be like stay there, right? Imagine it's a plain surface, but you have to give the accelerator to get it moved, right? So like that, in the lifecycle node, what happening is that you can simply start the node, and it's our choice to start the actual working of the node. Okay, means like it will be start doing some computation once we start it, and if we give some commands to stop it, it will be stopping the computation. Okay, so lifecycle nodes are like the node that we can change the sequence, or like sequence of the execution, like we can start it, stop it. Okay, but that is not possible in a normal node. I mean, we can actually make it, like we can program like that, but in lifecycle node it is already there. Okay, you will get an example for lifecycle node from GitHub. So basically the navigation stack is having a lifecycle node called BT Navigator Server. Okay, and that is actually it's actually yeah, so BT means behavior trees, and all these modules like controller server, planner server, behavior server, smooth server, all these things are communicating to the BT Navigator server. Okay, and you can individually configure the controller server, which is working on the controller part. The planner server is working on the planner part. Then behavior server is behavior trees, means like when you look back to ROS 1, there is no tool for sequence the motion of the robot. I will say an example. So in an application called full delivery, take the application food delivery. So in ROS 1, you are actually making a program like go to this location. Okay, then if it is successful, then wait for some time, then go to some other location, do this, do that. Okay, you have to write it. But in ROS 2, it's integrated with a thing called behavior trees. So you may have heard about the state machines. State machines are like you can sequence the actions of the robot. Like you can say like go to this position, and if the robot is going to some position, there are two outcomes. It may reach or it may not. Okay, so there is a true or false. So if it is successful, then do this. Okay, if it is failing, then do this. Okay, so the same behavior can be modeled using behavior trees. Okay, so it's a very very good method in order to sequence a navigation application. Okay, navigation application means like it's not like going to like one position and do some stuff. It's like go to one position and do some stuff, and based on the outcome do other stuff. Okay, so it's like doing many things, and like we are just sequencing the operation. So that is a main change happened to the ROS 2. It's called behavior tree, and there is a behavior server which is handling the behavior tree. Behavior tree we can sequence using program. C++ or Python program, or yeah, you can programmatically control the sequence. So this is actually the thing, and the input to the behavior trees are like map, sensor data, TF, and the behavior tree. Okay, so behavior tree is actually an input, because what is a behavior tree? It's actually having the sequence. Okay, how to move. Okay, which are the location to move, and what are the action it has to take, all these things. Okay, so this is what the nav2 stack, and the output, obviously the command velocity, which is going to the velocity smoother and collision monitor and the robot, to the robot base. Okay, the inputs are like the waypoints, set of waypoints. Maybe you can feed to the navigation stack, or like some autonomy system. Yeah, it can be, something that gives the waypoints. Okay, so this is an bird's eye view of the navigation stack, and you can also go through this website, and there are a research paper and a good video explaining exactly about the navigation stack too. And Steve Mackenzie, he's the author of it, main author. And yeah, so this is the an idea of the navigation stack. But if you think like what are the advantages that you are getting, I will say the behavior trees is an add-on, and all the other things like planner, it got improved, then slam got improved. So there are multiple improvements, and also it is we can easily put this into the product. Okay, so all these things are the improvements. So if you want to take this, you can start using it. So there is a module actually coming, like mastering navigation stack 2. So it will be discussing with a robot, and also we will be dive into the parameters. Okay, so so this is the idea, guys. Like we try to start the navigation stack, but unfortunately I think there are some bugs in it, and we couldn't able to show the demo. but I hope I can fix it and then I can show to you. So the simulation for the Turtlebot 3 is the same.
Sir.
Yeah, Kuljit, tell me.
Sorry to
No
interrupt.
problem.
Actually, I was also facing that same issue that map was not loading.
Yeah.
So how I solved it, I just saw the launch file of Turtlebot 3
Yeah.
simulation. I think it's a package that comes in with the Turtlebot
Yeah.
3. It's a demo package.
Yes.
So there I saw that they are using this nav to bring up.
Yes.
It it is a package.
Yes.
Now, so I just copied that launch file
Okay.
from where that nav to bring up was there, and then edited that launch file according to my directly. Like where they were using that rvs config, I replaced it with my rvs config, and that map file location I replaced it with my map file.
Okay.
So then it began to work, and I was able to load the map and perform the operation.
But here,
So that,
Kuljit,
that
you can also see here. Here, the map is actually loading. Okay, so like I just put the map. Maybe I can show you here. The map is actually loading and it is showing in RVs. Okay, so maybe we can check. I'm starting with the Lino board. Oh, sorry, 1 second. This was for the turtle board. 1 second. So I started the Lino board simulation, and I'm starting the navigation command for the Lino board. Second, yeah. So here, the the path, actually the playground map is on the home folder, and you can see it. The map is actually coming, but it's showing the TF issue. So here the map is loading, but the AMCL actually creating some problem. So you can see the issue. Maybe we can look at the first issue. This is the problem. AMCL cannot publish a pose or update the transform. Please set the initial pose. So maybe we have to set the initial pose maybe using the 3D estimate. I'm not sure. Yeah, it seems like that is the issue. Uh, See, Kuljit, um,
yeah, got it.
yeah. So it's
Initialization was the issue
basically,
here.
yeah, set the initial, but that is actually stupid because they can actually initialize with some value, because in ROS 1, we had an option to set the AMCL pose. So they can initialize the values with some value, but yeah. So here, if I'm giving, let's see what will happen if I'm, yeah, now it is showing the path. Anyway, like I mean, good to share your experience, because then only I just read the comment, because I'm trying this today only, this example. So when I was getting the issue, then I thought like, okay, fix it and then um, show some other time. But now it's clear, like it seems like it's the issue of the AMCL once it get the pose. So I was thinking like the project will be setting some initial pose, and yeah. So once it start, yeah, it will be. But yeah, seems like it is on some obstacles. Yeah. But it is planning the path, and okay, yeah, at least it's showing the path. Maybe I can change the pose estimate to here. Let's see. And there is a small I mean plugin here. It's showing the feedback got aborted, all this stuff. So it seems like Even with the 2D pose estimate, it is not changing the pose. Yeah, it's changing, but it's taking some time. And also, like, one problem that I'm seeing is the place where the robot is actually in an obstacle, it says. So that's why the robot is, robot can't able to move. So that is again tricky because there is no obstacle here around the robot. So maybe some other stuff interrupting the view or something. Maybe the robot itself detecting as an obstacle. Uh, yeah, I think there are some movements happening. Okay. Uh, yeah. So see, now that map got cleared and it's trying to move. Okay, so now the localization is lost. Yeah, that is interesting. So this is what, like, there are multiple issues. Maybe I can simply increase. Yeah, it's not because of the laser. Yeah, the robot itself detecting as an obstacle. That may be the issue. But it tried to move. Yeah, you can see here there is a local planner and the global planner is set. Yeah, it's moving. Hmm. Yeah, you can see it is trying to move anyway. Yep. Yeah, I think so. The navigation seems like working. We need to provide the initial pose. If you're providing the initial pose accurately, I think it will be okay. Okay. Okay, so I think we can conclude the session today, and I'm opening to the Q&A. Like, today I'm just concluding, like, the things that we have seen was, like, we have seen the construction of the robot, mainly the electronics, all the stuff. And I'm not explaining about the CAD and all, CAD models and all, because the main thing is electronics and the communication to the main computer. So we have seen the packages, SLAM package, and but we didn't explain. I mean, we didn't discuss the launch file that we will be discussing in the upcoming chapters, I think. But this is like a sneak peek into the navigation and the mapping. It seems like the entire pipeline is working, but we need to, like, tune it somehow. Okay. Okay, guys. So now the time for question. Let me know if you have any questions. Let me know if you have any question, guys. Any questions?
Yes.
Yeah.
In ROS one in our navigation stack, there was an option like to select the global frame and like, is there anything like that? Like
I mean,
we choose map as global frame.
no. See, actually, if you are doing the mapping and navigation, we are actually doing everything with respect to the map, right? So the global frame should be map. Okay, so this is how the TF looks like. If you are doing the mapping, 1 second. If you are doing the mapping or navigation, the robot is actually moving over the map. Okay, so the map is the reference, then the map frame to odom to the base footprint. So this is the frame of the robot, this is the odom frame, and this is a map frame. Okay, so this is a correct TF thing. So in the RViz, it's already put the map as the fixed frame here. Okay, so the fixed frame, all these frames assignments are the same as rows 1. Okay, only difference is they actually change the modules, then the technology, I mean they are using behavior tree to sequence the application. Okay,
The concept of move base that
yeah,
they removed, right?
move base, instead of move base we have like BT server, all these things came, BT navigation server. Okay, we will be,
So all the
yeah,
happening inside of this thing, right? Yes.
which one, can you say it again?
The localization, AMC, all these things are happening inside this BT, this lifecycle manager, right? Is it like
It's
that?
actually like a, like, I mean this is like an integrator, like all the things are connected or communicating to the navigation navigator server. Okay, AMCL is actually separate. In the navigation stack, we only like playing with the local cost map, global cost map, planner, then behavior trees, controller, all these things. But AMCL node is different. Okay,
Okay,
so
okay,
yeah,
yeah,
yes.
yeah, got it.
So yeah, because uh, talking about the navigation, I think we have to discuss a lot of stuff. So this chapter I aim to like give an idea, like if you are creating a robot or something, this is how the flow. Okay, this is how the flow. So like even if I am planning to create a robot, I will be looking for a reference, right? So we have a lot of reference. One of the reference is Lino robot. Okay, so you can because in Turtlebot we can't refer much about the hardware, but in Lino robot you can use the hardware and also the programming firmware also you can check. Okay. Okay guys, so that's it for today. I will be updating the session. So tomorrow, I mean next week, I will be planning for this. Okay, rows to ignition and webboards. Like we started with ignition, we have seen some Turtlebot 4 simulation, but it was not like we didn't complete it. So next week I'm planning to like show you the simulation of, I mean ignition simulator and also the web boards. Yeah, let's see. And for the ISAC simulator I will give you some idea, because I can't able to simulate ISAC in VMware. It needs some graphics card requirement. Okay, so that is the problem. Okay, so anyway, like I will be sharing it. So these are the 2 chapters that we are aiming, mainly the simulation. Okay, thank you for attending. See you next week.